Good morning all. Today we are going to see the design of field system in DC machines. In our previous video session we have studied about the design of armature winding and selection of number of armature slots. First I will give you an introduction about a DC field system. The DC field system mainly consists of pole core, pole shoe and field coils. That is the field winding. Basically there are two types of field windings. One is shunt field winding and the other one is series field winding. As the current flowing through the shunt field winding is very small, it is designed to have larger number of turns made up of thin conductors, whereas in the case of series field winding, the current flowing through it is quite large, which is same as that of the load current. Therefore, it is designed to have smaller number of turns made up of thick conductors. Generally, the field coils are former wound, insulated, and then placed over the pole cores. Next we are going to see the factors which has to be considered for the design of field winding and their typical values. The first factor is mmf per pole and flux density. The value of flux density in pole body is usually 1.2 to 1.7 Weber per meter square and is usually indicated as BP. B is the standard notation which is used for flux density. Since it is representing the flux density in pole body, we are putting a suffix P also here. Next is mmf per pole. The mmf per pole is usually represented as ampere turns of the field winding at full load. So we will indicate it by using the symbol ATFL, where AT is indicating the usual notation for mmf, and since it is that of the field winding, we are putting the suffix FL here. Generally the standard value of ATFL is 1.1 to 1.25 times that of the ATA, where ATA is actually the armature mmf at full load. So we can say that the field mmf at full load is actually 1.1 to 1.25 times that of the armature mmf at full load. Or else we can also say that the field mmf at full load is around 10 to 25 times greater than that of the armature mmf at full load. The next factor which is to be taken into consideration is the loss dissipated from the surface. We are representing it by the symbol QF. Q is actually the general symbol which we are using for the loss. Since we are considering the loss which is being dissipated from the surface of the field winding, we are using the notation F also here along with it. So QF is actually permissible loss per unit winding surface for normal temperature rise, and its value is 700 watts per meter square. Next major factor is resistance of the field coil, and the value of resistance of the field coil is decided by the material which we are used for the field coil. So while considering the material, we can say the resistivity as the parameter, and the typical value of resistivity is 2 into 10 raised to minus 8 ohm meter. The final factor which is to be taken into consideration is the current density, and its typical value lies between 1.2 to 3.5 ampere per millimeter square. Whenever problems are being asked, these values will be mentioned, but still it is better to remember the typical values. Now let's get into the design of a shunt field system. The design of shunt field system mainly involves the determination of these 6 parameters. The first one is dimensions of main field pole, that is the dimensions of pole core. Second is dimensions of field coil. Third is current which is flowing through this field coil or this field winding. Fourth is resistance of field coil. Fifth one is dimensions of field conductor. See, this dimensions of field coil and dimensions of field conductor both are entirely different. You will come to know that in the upcoming slides. And the last one is number of turns in field coil. We are going to see each one of them in detail. The first one is determination of dimensions of main field pole. Here two poles are shown. One is actually the rectangular pole and the other one is cylindrical pole. In this rectangular pole, you have to determine the height of the pole, length of the pole and width of the pole. Whereas in the case of this cylindrical pole, you have to identify the height of the pole and diameter of the pole. This is the standard relation of flux density in a pole body. If we know the values of BP and phi p, then we can easily determine the value of AP. In the case of circular poles or cylindrical poles, if we know the value of AP, we can easily find the diameter of pole by using the standard relation, that is pi r square or pi d square by 4. Another important concept which you must know is leakage coefficient, it is actually defined as the ratio of total flux to useful flux. The total flux from a pole body is represented by phi p, and the useful flux is indicated as phi. So from this relation, the value of AP can be easily written as AP is equal to CL phi divided by BP. So it's very clear that if the value of useful flux is known, leakage coefficient is known, and the value of flux density is known, then definitely we will be able to calculate the value of cross-sectional area of the pole. Once if it is known, we can easily determine the dimensions of the pole core. Now we are going to see the design parameter, dimensions of field coil. When rectangular pole core is being used, the field coil is rectangular in shape, whereas when cylindrical pole core is being used, the field coil is cylindrical in shape. This height of the field coil is depending upon the factor, the surface which is required for cooling the coil, and the number of turns in the coil. So both this HF and TF cannot be designed independently. TF is actually the turns which are present in the field coil, and HF is the usual notations which are provided for height of field winding. First, let's see the design of rectangular field coil in detail. So if we see in this diagram, the inner rectangle is representing the rectangular pole core, and the outer portion is indicating the rectangular field winding. The top cross-sectional view is indicated here. So this portion is actually the rectangular pole core, and the outside rectangle is the field winding one. You will be able to see very clearly here the dimensions of the pole body is marked. LP is the length of pole body, whereas BP is the width of pole body. Field windings are wound over this pole core, which will be having rectangular in shape, and the depth of the field winding is shown here. The outer length is usually represented by LO, whereas the inner length can be represented by LI, that is the length of the field winding. Then we will be able to easily obtain the value of mean turn length by adding or by taking the average of LO and LI. That is, if the lengths of outer turn and inner turn are known, then we can easily determine the value of mean turn length by taking the average of outer turn length and inner turn length. That is, the relation for LMT will be LO plus LI by 2. That is the length of mean turn when a rectangular pole core is being used, or when a rectangular field winding is being used. But more accurately, we will be using another relation to find the value of length of mean turn. The length of mean turn is indicated by this dotted line. So the length of mean turn can be written as LP plus DF by 2 plus DF by 2 plus BP plus DF by 2 plus DF by 2, again plus LP plus DF by 2 plus DF by 2, again B plus BP plus DF by 2 plus DF by 2. Adding all this together, we will be able to get the relation for length of mean turn as 2 times the addition of length of pole body, width of pole body, and 2 times the depth of field winding. You must remember this relation. In fact, you don't need to by heart this. Once if you know how to draw this diagram, then from this diagram you can deduce the relation by yourself. Similarly, in the case of cylindrical poles also, the length of mean turn is indicated by the circle. So you have to find the circle's perimeter to get its mean turn. So it's very clear that the diameter of this circle is dP plus dF by 2 plus dF by 2, where dF is actually the depth of this field winding. This whole diagram is indicating the top cross-sectional view of this cylindrical field winding. The inner circle is indicating the pole body, that is a cylindrical pole body, and the cylindrical winding is wound over it. So the depth of field winding is indicated by dF, and the length of mean turn is shown by this dotted line. So in order to get the value of length of mean turn, or in order to get the relation for length of mean turn, you have to obtain this dotted circle's perimeter. So the radius of this dotted circle is actually dp plus df by 2, or else the diameter can be said to be, the radius is dp by 2 plus df by 2, and the diameter can be said to be dp plus df. Therefore the length of mean turns relation can be written as 2 pi into dp by 2 plus df by 2, or else we can write the relation as, that is after cancelling those two 2's, we can write the relation as pi into dp plus df. That is actually the relation for length of mean turn in the case of a cylindrical field coil. Just like I have mentioned before, the height of this field coil is having dependency on the surface required for cooling the coil as well as the number of turns of the coil. Therefore this HF and TF, that is both height of field winding and turns of field winding, cannot be designed independently. So in order to solve the values of HF and TF, two equations are required. You will come to know that in detail while solving a problem. Now the third parameter is current in shunt field winding. If the voltage across a shunt field coil is known and the resistance value is also known, then we can easily determine the value of current which is flowing through that shunt field coil. That is the current which is flowing through that shunt field winding. In a shunt DC machine, each pole of the DC machine carries a single field coil, and all these field coils are actually connected in series to form the shunt field winding. Therefore voltage across each field coil can be determined by dividing the total voltage across the shunt field winding with the number of poles as indicated in this relation. But this voltage across the shunt field winding will not be same as that of the terminal voltage under loaded condition. This is due to the drop which is occurring in armature resistance, brush drop and armature reaction. So considering this effects of the drop, the voltage across the shunt field winding is usually taken as 80 to 85% of the rated terminal voltage. Hence this relation can be modified as 0.8 to 0.85 times V divided by P. The fourth design feature is the dimensions of field conductor. The second design feature was the dimensions of field coil. There we had identified the values of length of mean turn, height of field coil and depth of field coil. But here we are mainly going to identify or determine the diameter of the field coil. That is, the dimensions of field coil are mainly area of cross section and its diameter. So from the known values of the field current and the current density, we can easily determine the cross sectional area of the conductor. Once if the cross sectional area of the conductor is known, we can easily determine the diameter of field conductor by using the standard relation pi d square by 4, and the diameter of field conductor is indicated by DFC, diameter of field conductor. Either the value of cross-sectional area can be determined by using the known values of field current and current density, or else if the values of EF and resistance, the relation for resistance you know, rho L by A. So by making suitable substitutions in the basic Ohm's law, that is V is equal to IR. So in that R, if you are making the substitution rho L by A, from which you can easily get the relation for cross-sectional area of the conductor. Since we are determining here the cross-sectional area of the field conductor, we will be representing it as A suffix small f. IF is the current which is flowing through the field conductor, rho is the resistivity. The total length can be identified by multiplying the mean length with the total number of turns which are present in the machine. So TF into length of mean turn will be giving you the actual length of the field conductor, and the voltage is indicated by EF, which is actually 80 to 85% of that of the terminal voltage. Usually these conductors are coated with varnish in order to provide insulation to the conductors. Therefore the diameter of field conductor while considering this varnish insulation also will be the sum of diameter of field conductor and the thickness of the insulation. Next we are going to define copper space factor. it is given by the relation 0.75 into square of the ratio of diameter of field conductor excluding insulation to the diameter of field conductor including insulation. It is usually represented by SF. It can also be found out by using another relation, that is the net copper area divided by the total copper area. If we know the cross-sectional area of this field conductor, and if we know the total number of turns which are present in this field coil, then definitely we can easily find the net copper area by multiplying AF with TF. But usually all these conductors in this group of field coil are wrapped together with a tape. You will be able to see that in the left side of this pole core. In the right side we have shown it without the tape, but in the left side we have shown it all these three conductors being wrapped together with a tape. So we will be able to find the total area by simply multiplying this height of field winding with the depth of the field winding. So this indicates the total area, and while taking the ratio of net copper area to total area, we will be able to identify we will be able to get the value of copper space factor, which is usually indicated as SF. The next feature is the number of turns of field coil. The number of turns of field coil can be easily determined by using this relation. In this relation, the numerator is indicating the field MMF, whereas the denominator is indicating the current which is flowing through the field coil or the field winding. From this too, we can easily determine the value of number of turns which are present in this. Next we are going to see the power loss in the field coil. The power loss in the field coil is occurring due to the I square R loss. Heat developed due to this power loss is dissipated through the surface of the coil. Heat will be dissipated through the outer surface, through the inner surface, through top surface as well as the bottom surface. That is, heat will be dissipated through all the four sides of the coil. The outer surface area is calculated by multiplying the height of the field coil with the term length of mean turn plus 2 times the depth of field coil. When we are adding 2 times depth of field coil with the mean turn length, we will be getting this outer perimeter of this rectangle. And while multiplying it with the height of the field coil, we will be able to obtain the outer surface area of the field coil. Similarly, the inner surface area of the field coil can be obtained by multiplying the height of field winding term with length of mean turn minus 2 times the depth of field winding. Those two relations are given here. Both top and bottom surface area can be easily calculated by multiplying the mean turn length with the depth of the field winding. So by adding all this, we will be able to get the total surface area of the field coil, and it is found to be 2 times length of mean turn into height of field winding plus depth of field winding. Once if you know this diagram and its indications properly, then you don't need to by heart these relations. You can deduce these relations from this diagram itself. We have already discussed in the factors which is taken into consideration while design of the field system, that is while design of the field winding, that the permissible loss per unit area is usually indicated by Q suffix small f, small q suffix small f. The total loss dissipated from the field coil is given by capital Q suffix small f. This value can be easily obtained by multiplying small q suffix f with the total surface area, because the small q suffix f is actually indicating the heat loss per unit area. So while multiplying the heat loss per unit area with the total surface area, we will be able to obtain the value of total loss which is dissipated through all the surfaces of the field coil. So instead of this S, we can make the substitution 2 into length of mean turn into HF plus DF into QF. As we all know, the standard relation of copper loss is I square R. So instead of this IF, we can make the substitution EF by RF, then the relation gets modified into this form. Further, instead of RF, we can make the substitution rho length of mean turn into number of turns in field winding divided by cross-sectional area of the field winding. Further simplifying it, we will be able to get the relation like this. This is actually the standard relation of copper loss in the field coil. Both this copper loss and the copper loss or the heat loss or the power loss which is dissipated through the surface of the field coil, both this are one and the same. So equating this two, we will be getting a relation, and it is indicated here as 1. As we have seen before, the height of field winding and the number of turns which are present in the field coil both cannot be designed independently. So in order to find this values of this HF and TF, we have to create two equations relating these two terms. Then further solving those two equations, we can easily find the values of HF and TF. By equating this power loss terms, we have formed the first equation. The second equation can be obtained from the copper space factor relation. That is, from the standard relation of copper space factor, we very well know that SF is equal to AF TF divided by DF HF. From this, we will be getting the relation between HF and TF. That is also mentioned here, and it is marked as equation number 2. So while solving these two equations, we will be able to obtain the values of HF and TF. Please note a correction here. While solving these two equations, we will be able to obtain the value of HF and TF. It's not DF, it's HF and TF. Now I will just summarize the step-by-step procedure followed for the design of shunt field winding. The first step is we will be assuming a suitable depth for the field winding. That is, a suitable value is assumed for DF. In step 2, we will be identifying the dimensions of the pole. The dimensions of the pole are actually the cross-sectional area of pole and the diameter of the pole if it is a cylindrical pole. Whereas in the case of rectangular pole, we will be finding out the length of the pole and width of the pole. Similarly, the height of the pole also can be identified. Next, I am going to explain the step-by-step procedure followed for the design of shunt field winding. The first step is we will be assuming a suitable depth for the field winding. That is, a suitable value is assumed for DF. In the second step, we are going to find the dimensions of the pole. In order to identify the dimensions of the pole, we will be provided with the values of BP and phi p, from which we can get the value of AP, which is actually the cross-sectional area of the pole. If the pole is cylindrical in shape, very easily we can find the diameter of the pole from the area of the pole using the standard relation A is equal to pi d square by 4. While in the case of rectangular pole, we have to identify its length and width of the pole. So while considering the length of the pole, we can consider the iron length or the active length of the pole. Due to the effect of this slotting, the net iron length of the pole is actually 0.9 times the actual length of the pole. This is due to the effect of slotting. Once after the net iron length of the pole is identified, we can easily calculate the width of the pole by dividing the area of the rectangular pole with the net iron length of the pole. So in step 2, we have determined the dimensions of the pole. In step 3, we are going to determine the mean turn length both in the case of cylindrical pole as well as rectangular pole by using the standard relation. We have already obtained the standard relation. Next, in step 4, we will be identifying the voltage across the field coil, that is across each of the field coil. As these field coils are connected in series, in order to identify the voltage across each field coil, we have to divide the total voltage which is being applied across the field winding with the number of poles. Since the total voltage which is applied across the field winding is not same as that of the terminal voltage, this is due to the effect of drops which are occurring in the DC machine. It will be brush drop, armature resistance drop and armature reaction drop. So taking that also into consideration, we will be able to identify the relation for voltage across each of the field coil as this one. We have already explained it in detail before. Next, by using the expansion relation for resistance in Ohm's law, we will be able to identify the cross-sectional area of field coil. Actually, the relation for current with the Ohm's law is V by R. Instead of R, we will be making the substitution rho L by A. Then from which we will be able to obtain the value of AF, that is actually the cross-sectional area of the field conductor. Once if the cross-sectional area of field conductor is known, we can easily determine its diameter by using the standard relation pi d square by 4. So this DFC is indicating the diameter of the field conductor. This will be the diameter of the field conductor without insulation. As I have mentioned before, usually a varnish insulation will be provided. So while taking this varnish effect also into consideration, the effective diameter will be DFCI. Hence the copper space factor relation can be easily identified if we know the values of DFC and DFCI. In step 7 we are going to solve the values of TF and HF. In order to solve the values of TF and HF, we cannot just identify it independently. So we have to form two relations in TF and HF. That two relations are shown here. This is also explained before. While solving these two relations, we will be able to get the values of TF and HF. In step 8, we will identify the resistance of field coil by using the standard relation rho L by A. All these 8 steps which I said now is actually the calculation steps which you have to follow for a perfect design of a shunt field winding. Now you have to verify the calculated values which you have obtained is correct or not. For that some checks are there that we are going to say in the upcoming steps. The first step is, or the first checking step is, you have to calculate the value of current density and you must ensure that its value is less than 3.5 ampere per millimeter square. From the steps mentioned from 1 to 8 we know the values of IF and AF. So we can easily calculate the value of current density and see if its value lies less than 3.5 ampere per millimeter square. If it's not lying less than 3.5 ampere per millimeter square, means definitely you have to increase the value of AF and you have to repeat the steps from 6 to 9 so as to ensure that the value of del F is lying less than 3.5 ampere per millimeter square. Further, if the value is still not less than 3.5 ampere per millimeter square, means you have to again increase the value of AF by 5%, and then again you have to repeat the steps from 6 to 9. Next check is you have to see if the field MMF is 10 to 25% greater than that of the armature MMF. If it's not, then you have to increase the value of depth of the field coil by 5% and you have to repeat all the steps from 3 to 10 till this condition is being achieved. That is, once if you are checking and finding that this condition is not satisfied, means you have to increase the depth of field winding, the assumed depth of field winding by 5% and you have to repeat steps from 3 to 10, and further you are seeing that this condition is yet not satisfied, means again you have to increase the depth of field winding further by 5% and you have to repeat all the steps. Next check is the temperature rise of the coil. The temperature rise can be easily identified by using the relation QF into C by S. We have already studied this relation in our temperature rise video session. That was our second video session. There we have studied that the relation for temperature rise was theta m is equal to Q by S lambda, and that 1 by lambda can be replaced by C. So the temperature rise relation will be QC by S, where C is actually the cooling coefficient and its relation is also given here. So you have to calculate the value of temperature rise and you have to see if the temperature rise is within the safe limits or within the specified limits. If it's not, means again you have to increase the depth of the field coil, that is the assumed depth of the field coil, and you have to repeat all these steps further. The steps followed for the design of series field winding is same as that of the steps followed for the shunt field winding. The series field winding will be used both in the cases of series machine as well as compound machine. The only difference which you must remember is in the case of compound machine, the MMF to be developed by the series field is only 15 to 25% of the full load armature MMF. In previous case it was not like that. In the case of shunt machine, the MMF to be developed by the shunt field winding was 10 to 25% more than that of the armature MMF. Whereas in the case of a compound machine, the MMF to be produced by the series field winding is actually only 10 to 25% of the armature MMF. The remaining 100% will be formed by the shunt field MMF. So you must keep that particular point in your mind. This was the case only with the case of compound machine. Now let's see some problems which are associated with the design of shunt field winding. Let's see the first problem. In this problem, it's actually a shunt field winding design. The machine parameters are given. The rated voltage is 440 volt. It's a 6-pole DC generator. MMF per pole is given as 7000 ampere. Depth of winding is given in the problem itself, so you don't have to find that. DF value is given. Length of inner turn is given. Length of outer turn is given. If the inner turns length and outer turns length are given, means mean turn length can be easily identified by taking the average of these two. The loss radiated from the outer surface excluding ends is given. That is the value of small qf. It's clearly mentioned that the loss is getting radiated only from the outer surface. There is no mention about the top surfaces or inner surface. So whenever you are seeing this loss radiated from, means specifically you have to see from which surfaces they are given in the problem. If you are using the standard relation for total surface area, means you will be getting this answer as a wrong one, because here it is specifically mentioned that the loss is radiated only from the outer surface. Space factor is given and the resistivity is also given. So in the first step, we will identify the value of voltage across the shunt field winding, which is around 80% of the rated terminal voltage, that is 352 volt. Now voltage across each coil can be easily identified by dividing it with the total number of poles. So now we have obtained the voltage across each field coil. Now the mean turn length can be easily obtained by adding this 2 and dividing it with 2, which is found to be 1.25. Area of field conductor can be identified by using this relation. All these parameters are knowns. So the value of cross-sectional area of field conductor is 2.98 millimeters square. From this we can determine the value of DFC, that is the diameter of the field conductor, because this is equal to pi by 4 DFC square. Next we have to determine the values of TF and HF. As TF and HF cannot be determined independently, we have to form two relations in TF and HF. So the first relation can be obtained from the standard relation of copper space factor, that is TF AF is equal to SF HF DF. Please note the correction. Here it is not EF, it is AF. The substitution what they have done here is the correct one, but in this relation they have written it as wrong. It is actually AF. Previous also I have explained it very clearly. See, this is the relation TF AF is equal to SF DF HF. So that same relation is being used here, and we will be able to obtain a relation between TF and HF. Next relation is obtained by using the power loss relation. As the power loss dissipation is occurring only through the outer surface, we have to first find the outer surface area. Outer surface area is L0 into HF. The value of L0 is given. The heat dissipated per unit surface area is given in the problem itself. It is actually 1400 watts per meter square. So the heat which is getting dissipated through the total outer surface area can be easily obtained by multiplying it with the total outer surface area. So we got the value of QF as 1960 HF. The field current can be found out by using the relation QF divided by EF. In this we will be able to get a relation in IF and HF. In the question, the MMF per pole is clearly given as 7000 ampere. So the MMF relation is actually ampere turns. You can easily find the ampere turns by multiplying IF with TF. So we have already obtained IF in terms of HF. So while multiplying IF into TF, we will be able to get a relation in HF and TF, and its value is given in the problem as 7000. So by solving this relation in TF and HF and this one, we will be able to identify the values of TF and HF, and it is found to be 1475 and 0.142 meter. So by this we have solved all the physical dimensions of the field coil, that is height of field coil, depth of field coil is given in the problem itself, diameter of field conductor, and the total number of turns which are present in the field coil. In this problem, only the design of shunt field winding is being asked. It's not asked anything about the design of poles or the dimensions of the poles. So we have neglected the first few steps which we discussed before in the design of field system, because the first few steps was associated with the dimensions or determination of the dimensions of the poles. Now let's see the next problem. This problem is also similar to that of the previous one. Shunt field coil has to develop an MMF of 9000 ampere. Voltage drop is directly given as 40 volt. Resistivity of round wire is 0.021 ohm per meter and millimeter square. Depth of winding is given in this problem also, and length of mean turn is also given directly, so you don't have to find that. You are asked to find the design of a coil so that power dissipation is 70 watts per meter square. Take the diameter of the insulated wire is 0.2 mm greater than that of the bare wire. So this is actually given to find the value of copper space factor. Let's see the solution. We can easily determine the cross-sectional area of conductor by using this relation. So in this relation, this is actually indicating the field MMF. The value of field MMF is given in the problem directly as 9000 ampere. Make the substitution. Value of EF is also given directly as 40 volt. Then we can easily get the cross-sectional area of the field conductor, from which we can directly get the value of diameter of the bare conductor. Once if the diameter of the bare conductor is known, we can get the diameter of the insulated conductor by adding it with 0.2 mm. If we know these two terms, means we can easily solve the value of space factor, that is a copper space factor, by using this relation. Now using the equation of copper space factor, that is SF HF DF is equal to TF AF, we can get a relation in HF and TF. The second relation is depending on the total loss which is being dissipated from the total coil surface. Here it specifically mentioned total coil surface. So we have to find total coil surface first. The relation for total coil surface area is 2 into length of mean turn into HF plus DF. So by multiplying this total surface area with the heat dissipated per unit area, we will be able to get the total loss from this surface in terms of HF. And another equation of QF is IF square RF. By simplifying this, that is making the substitution of RF and all, we will be able to get the relation in terms of TF. So this term and this term are one and the same, because if you see in both this equation, the left hand side is capital QF. So you can easily equate both of them and you will be able to get another relation in HF and TF. So solving the two relations in HF and TF, the one which we got from the copper space factor and the other one which we got from the copper loss, we will be able to solve the values of HF and TF as 0.15 meter and 933. With that, we are completing today's session. Usually in the university question paper, the design of shunt field winding are asked regularly. So please practice more questions from today's session. Thank you.